All right, let's get started. The first thing I want to say today is that there is an exam coming up, and it will be next week. So next week, Wednesday and Friday will be the third exam. So, and we'll do it just like we've done the other exams where I think it's groups, what is it? A and C, is it, that would go on Wednesday, and then group B on Friday. We'll just keep it the same. So kind of the schedule up till then is today we're talking about the mean value theorem, and you'll turn in that homework. Friday we'll talk about L'Hopital's rule, and you'll turn in that homework. And then Monday will just be a review day, and we'll kind of talk about things and go over what will be on the exam. And then Wednesday and Friday will be the exam. And then we just have like a couple more weeks. So there will be an assignment assigned for next week that will be due the following Monday. And then we'll talk about that one on Monday. And then we have like 4 more sections. So 2 each week. And then that will finish up chapter 5. Then we'll have our final. So that's kind of the rest of the semester. It's going quite quickly. Yeah.
Is the final be comprehensive?
It will be, yes. The final is comprehensive. And so basically there might be like a slight leaning towards the last chapter, just since we won't have had any exam over the last chapter that's over integration. But generally it's pretty much equal across the board. Yeah. So so just one more time, especially for people maybe just joining online or something. Exam 3 is next week, Wednesday and Friday. So a week from today, we'll start exam 3, and Monday will be review day. Okay, any other questions before we get started with actual math questions? Okay, any homework questions then? Yes, sir. 19? Okay. Okay, so 19 says lapse rates in the atmosphere refer to example 2. Concurrent measurements indicate that at an elevation of 6.1 kilometers, the temperature is minus 10.3, and at an elevation of 3.2 kilometers, the temperature is 8 Celsius. Okay. Based on the mean value theorem, can you conclude that the lapse rate exceeds the threshold value of 7 at some intermediate elevation? Yeah, okay. So this question sounds complicated, but it's really not. So what does the mean value theorem really say? So what's the mean value theorem say? So let's see, just a second. Example 2. I guess I should actually look at it. Example 1, 2, okay. Okay, so it's like the change in temperature over altitude is the lapse rate. Okay, elevation. Okay. So let's write down what we know here. So this is number 19. It tells us that basically a lapse rate is the change in, is it temperature over altitude? Okay, so it's like the change in temperature over altitude is what we call this lapse rate. Okay, so it is a derivative, which is helpful since we're using the mean value theorem. Okay, so now what do we know? We know that at an elevation of 6.1 kilometers, we have a temperature of negative 10.3 degrees Celsius. Okay, and we also know that at an elevation of 3.2 kilometers, we have an elevation, we have a temperature of 8 degrees Celsius. Okay. So based on the mean value theorem, can you conclude that the lapse rate exceeds 7 degrees per kilometer at some intermediate elevation? And then explain. Okay. So first of all, just what does the mean value theorem tell us? So this is a change in temperature over basically elevation, right? And so what is, if this is like our point, so you can think of this as dy dx. So the y is the temperature and the x is sort of the elevation. So this is kind of like my x1 and my y1. This is kind of like my x2 and my y2. And what does the mean value theorem actually say? The mean value theorem says that somewhere in between, like if you're over here and you have a point x1, y1, and you have a point x2, y2, maybe I should have actually graphed those well. But what it says is if you figure out what the slope is in between those 2 points, then somewhere the curve, if there was a curve between these two guys, somewhere the curve has the same slope, correct? At some point C. So we have 2 points. And so we could figure out, well, what happens, what slope do we know that this curve has? So let's see. So we say that like our function, its derivative at some point C is equal to y2 8 minus y1, which is minus 10.3, divided by x2, 3.2, minus 6.1. Okay, so f prime c is equal to, well, what do we have? This is positive 18.3. And on the bottom, we get minus what? 2.9. Okay. And so what do we end up with here? Anybody have a calculator out handy?
Negative 6.03 or 6.31. I apologize.
Negative 6.31.
Correct.
Okay, so what this tells me is that somewhere between these 2 points, the lapse rate, as I call it, is negative 6.31. That's what I know for sure. Am I given any more information than that? It says, can you conclude that the lapse rate exceeds the threshold of 7 at some intermediate elevation? And then explain. Well, what I would say is I don't know that. I don't know that it exceeds 7. And the reason why I can say that is, like, all that I know for sure based on the data that I've been given is that somewhere the slope is this, right? I don't really know how much it wiggles around. It could be identically this slope. And if it were identically that slope, well, it certainly never is 7 or above 7, right? So there's nothing really telling me. Now, if I knew that there was another place where it had a slope, let's say, that was bigger or something or smaller, maybe I could say something, but based on the data, I don't think that I can make that judgment. All that I know for sure is there is a place where the slope is negative 6.31. That's all I can say for sure by the mean value theorem. Does that make sense? So I know that, but that's all I know. Okay. Any questions on that?
So you don't have to find a point on the curve that has that slope. You just have to prove there is.
Well, you don't even have to prove there is. Basically, this is given by the mean value theorem that there is such a point. And that's all I really know by the mean value theorem, is that there is a point where the slope is negative 6.31. And they're saying, is there a place where the slope exceeds 7? And I'm like, based on that, I have no idea. Because it could wiggle all over the place, right? It could go where the slope gets really big or the slope gets really small. I don't really know. All I know for sure is there is a place where the slope is negative 6.31, and that's it. So if I were explaining this, I would say, all I really know by the mean value theorem is there does exist one point where the slope is negative 6.31, which is not bigger than 7. So I don't know. That doesn't mean there isn't. That doesn't mean there is. We just can't conclude one way or the other. Okay? Any other questions?
35, I believe.
35?
Yes.
Okay. So another inverse tangent, identity, use derivatives to show that tan inverse of 2 over x squared and tan inverse of x plus 1 minus tan inverse of x minus 1 differ by a constant. Okay. That's kind of cool. Okay, so this is 35, part A, let's say. And they're saying, let's look at the derivative. Let's say that f of x is tan inverse of 2 over x squared. And let's say that g of x is equal to tan inverse of x plus 1 minus tan inverse of x minus 1. Okay, and they say show that those guys differ by a constant. So the way that we're going to do this is we're going to use the constant difference theorem. Hopefully everybody's watched the videos, and in the videos I show 4 theorems, correct? There's Rolle's theorem, mean value theorem, zero derivative theorem, constant difference theorem, right? Okay, so what this is asking you to use is the constant difference theorem. So all that I have to do to show that 2 functions differ by a constant is show that they have the same derivative, right? That's what the constant difference theorem says, is if 2 functions have the same derivative, then they are the same function except for a constant. So if I could just show that these 2 functions have the exact same derivative, I'm done. Does that make sense? So that's all we really need to do, is show that the derivative of f and the derivative of g are the exact same thing. Okay, so let's try it. So we have f prime of x is equal to, so the derivative of tan inverse of something is 1 over 1 plus the thing squared, right? So this is 1 over 1 plus whatever's in here, 2 over x squared, quantity squared, times the derivative of what's inside. let's see, what's the derivative of 2 over x squared? That's the same as 2x to the negative 2. So it's negative 4x to the negative 3. So negative 4 over x cubed. Okay, and that is the derivative. So let's just leave it there for a second. And now let's work on the other one. And then we'll probably have to do a little bit of work to show they're actually the same thing. So let's go to this one. So if I take g prime of x, this is equal to, let's see, this is 1 over 1 plus this thing squared times the derivative of what's inside, but that's just 1. And then I need to take the derivative of this one, so I get a minus 1 over 1 plus x minus 1 quantity squared, and again, multiplied by 1. Okay, so if I could show that this thing and this thing are actually the same, I would be done. They don't look that nice, but I think we could probably do it. Okay, so let's work on this one a little bit. What do we have? So on the top, I get negative 4, correct? So there's a minus 4 on top. On the bottom, what do we have? Okay, we got to be a little more careful. So I'm multiplying, the negative went with the 4 on top. X cubed times 1 is x cubed. And then I get x, this is 4 over x to the 4th. So if I multiply that by x cubed, there's an x to the 4th on bottom, an x cubed on top. So there's just going to be an x on the bottom. What's going to be on top? So if I square this 2, I get a 4. So I get a 4 on top, and I believe I just get an x on the bottom. Is this believable? So think about that for a second. This thing right here is 4 over x to the 4th. Then I multiply it by x cubed. So it's 4 over x. Okay, that looks okay. Now we need to work on this bottom one. Multiply, what's that again?
Multiplying both sides by each other's denominator.
Yeah, it might be okay. I think I want to do a little bit of work first. By the way, I want to do one more step here, because let's combine these into one fraction. Okay, if I do, I get minus 4 on top, and on the bottom it would be, I could multiply this one by x over x, so I get x to the 4th plus 4 divided by x. Then I could flip and multiply, right? Am I running out of space on the video? I think I am. I need to be careful. Let me just move over here. So that says that the f prime of x is equal to, if I flip and multiply, I get an x on top. So I get minus 4x. And then on the bottom, I have x to the 4th plus 4. And I like this because it's just one nice fraction. Okay, now let's see if I can work on g prime of x and turn it into the same thing. So g prime of x is equal to, let's square out both of the bottoms. So if I do, I get 1 over 1 plus, and then if I square x plus 1, then I get x squared plus 2x plus 1. And then on the other one, I get minus 1 over 1 plus, and then I get x squared minus 2x plus 1. X squared minus 2x plus 1. So far, so good? Okay, I'm gonna want to combine these two eventually, but first let's simplify a little bit more. I get I get x squared plus 2x plus 2. And on this one, I get minus 1 over x squared minus 2x plus 2. Okay, so now I do need to combine these two into one fraction. So that's not like the best thing I've ever done in my life, because the only way to really do it is the common denominator is these two multiplied by each other. Okay, so, but we can do it. So this is equal to, if I multiply the top and bottom by this guy, then I'm going to get x squared minus 2x plus 2 over x squared plus 2x plus 2 times x squared minus 2x plus 2. And then on the other one, I get minus, and then on top, I'll get x squared plus 2x plus 2 divided by x squared plus 2x plus 2 times x squared minus 2x plus 2. Okay, remember the goal is that thing, right? Right now it looks kind of bad, but I think it will get nice soon. Okay, so what I need to do now is combine these. Notice now they have the same bottom, which is good. So this is up here, this is equal to, but if I combine the top, I get x squared minus x squared. So the x squareds cancel. I get 2 minus 2, so the 2's cancel. And then I get minus 2x minus 2x. So the top becomes minus 4x. And that is very promising, correct? That's what we wanted to be on top. Now let's multiply out the bottom. And I would really like it to be x to the 4th plus 4, but let's see what happens. So the bottom, I can combine this, and it's just this thing. So let's multiply it out. I get x squared times x squared is x to the 4th. Then I get x squared times negative 2x, which is negative 2x cubed. Then I get x squared times 2, which is 2x squared. Then I get 2x times x squared, which is 2x cubed. Then I get 2x times 2, which is 4x. Then I get 2 times x squared, which is 2x squared. Then I get 2 times negative 2x, which is minus 4x. And then finally, I get 2 times 2, which is 4. Okay. And the question is, do wonderful things happen? I hope so. I feel like some things cancel. Did I do one thing wrong? That's the question. Because I feel like this guy and this guy should cancel each other out, but I said that they do not. Let's see if I did something wrong. So the second thing I got was a negative. The third thing I got was a positive. That's right. The fourth should be positive. The fifth should be 4 negative. I should have a negative 4x squared. Where did that go? 1, 2, 3, 4, 5, 6, 7. Oh, I missed one. I don't know how I did that, but I somehow left one term out. Yeah, right in here. I should have had a minus 4x squared and then plus, that's right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right.
And that positive 4x should be 4x squared. No, never mind, I apologize.
I think it's okay. Now, let's see. So these guys cancel. Then I get 2x squareds, 4x squareds minus 4x squareds. The x squareds are gone. I get a 4x and a minus 4x. Those are gone. And I'm just left with minus 4x divided by x to the 4th plus 4, which is this guy. So they are equal. And that means that the original guys just differ by a constant. So f of x and g of x differ by a constant by the constant difference there. And that's it. That's a pretty cool problem, actually. I don't know if I've ever done that one before. I like that. Other questions? Yeah.
23.
23. Okay, so we want to determine whether the mean value theorem applies to the function on that interval. Okay, so we have f of x is equal to negative 2x if x is less than 0, and it's x if x is greater than or equal to 0 on the interval negative 1 to 1. And the first thing that they ask us to do is determine if the mean value theorem applies to the following functions on the interval. Okay, so I think let's draw this really quick and see what we think. So first of all, we get f of x is negative 2x if x is less than 0, and negative 2x, so the slope is minus 2. So we get the rise is minus 2, and the run is 1. So, and that is if x is less than 0. So it kind of goes this way. And then x if x is greater than or equal to 0. So, and that's on the interval negative 1 to 1. So everything past that is gone. Let's see, that should go up high on that one. It just doesn't look quite right. That seems better. Okay. That looks good. There's negative 1, there's 1. Okay, so here's my little graph, and I don't have this piece. And the question is, does the mean value theorem apply for this function? Now, what has to be true for the mean value theorem to apply? So if you go back to the mean value theorem, you look at it, yeah.
Isn't it the slope? There exists, the slope is 0 at some point.
Okay, not necessarily. So the mean value theorem basically, first it starts out with some conditions. It's like the mean value theorem only works under certain conditions. And so this is asking, does it satisfy those conditions? And does anybody know one of the conditions? Yeah.
The function is continuous.
Yes. First one is that the function is continuous. So is this function continuous? Yeah, it actually is continuous. What's another condition of the mean value theorem?
Is it differentiable?
It's differentiable. Is this function differentiable all the way along the curve? Or in other words, does it have a slope at every point? I'm seeing a lot of nods, yes. What about at this point? What's the slope? No, it's not 0. So it's a sharp point. And remember, one of the reasons that something might not have a derivative is because there's a sharp point. And one way of thinking about that is, what's the slope right here? -2, right? And what's the slope right here? -2, -2, -2. So if I take the limit of the slopes as I come in from the left, what does it look like the slope should be? -2. What if I did it on the other side? What's the slope here? 1. What about here? 1, 1, 1, 1. So on the right side, it looks like the slopes are getting close to 1. On the left side, it looks like the slopes are getting close to -2. So in the there is no limit. So this thing, there is no derivative at 0. And since there's not a derivative at 0, the function's not differentiable over the interval. And so the mean value theorem doesn't apply. And that's the end. So you just need to say, since there's no derivative at x equals 0, the mean value theorem doesn't apply to this function over the interval. And that's it. Other questions? Yeah.
29.
29. Okay. So on this one, same sort of thing. We want to figure out, does the mean value theorem apply over that interval? Okay, so we have f of x equals sine of x from -π/2 to π/2. So f of x equals sine x from -π/2 to π/2. Okay, and the question is,
27.
oh, I'm sorry. You're right. Sine inverse of x from 0 to 1/2. Sine inverse of x from 0 to 1/2. Okay, so here's the question. What does the function sine inverse of x look like?
So the sine graph, so it's like,
Yeah, it's kind of like sine flipped on its side. So sine looks like this, right? This is basically the sine wave. And then what I should do is flip it across that, do a mirror reflection over that. So what would it look like? So it looks something like the mirror reflection would do this. But sine, this isn't what I just drew, that's not a function, correct? So we don't include all of that. What do we include? Well, we let it get up to its highest point. We let it get down to its lowest point. But that's it. So over here, sine of what gives me 1/2? Sine of what angle is 1/2? I don't think so. Pi/6, right? Pi/6. So what we're doing is we're basically going, and sine of 0 is 0. So 0 is 0. So sine inverse of 0 is also 0. And then we're going until we get to pi/6. And that will give us the 1/2. Okay, so we're basically our interval here. Oh, I'm sorry, I did it the opposite way. That's bad. So I'm going from 0 to 1/2, and that will give me pi over 6. That's better. Okay, so this is what my little graph looks like. It's not very big, and I didn't draw very big, but you can kind of see what's going on here. And the question is now, okay, on that interval, is it continuous? Sure, yeah, it's nice and continuous on that interval. Is it differentiable? Yeah, can I take the derivative of sine inverse of x? Yeah, we know how to do that. And so it's differentiable on the interval, no sharp corners, no jumps, no discontinuities. It's all good. So yeah, the mean value theorem does apply on that interval for that function because it is continuous and differentiable. Okay, first part done. If so, what are the points that are guaranteed to exist by the mean value theorem? All right. So this one is a little more interesting. We have to find some things. So we need to know what's guaranteed by the mean value theorem is that there's a derivative value in between 0 and 1/2 such that sine inverse of 1/2 minus sine inverse of 0 over 1/2 minus 0 is equal to that derivative. Okay, so let's calculate what this derivative should be. So sine inverse of 1/2 we said was what? Pi over 6. So this is pi over 6. And then sine inverse of 0 is just 0. So minus 0 over 1/2. So again, this is pi over 6 divided by 1/2. I flip and multiply, and I get pi over 3. Agreed? Okay, so pi over 3 is the magic derivative value that I'm looking for out of the mean value theorem. The mean value theorem says somewhere in this interval, the slope is pi over 3. And then the question is where? So to figure out where, I need to find out what is the derivative of sine inverse of x. And we know that one, right? So f prime of x is going to be equal to 1 over the square root of 1 minus x squared, correct? And the question is where in between 0 and 1/2 is this thing equal to pi over 3? Or maybe a better way of writing this is maybe not the best, is I know that f prime of c, which is 1 over square root of 1 minus c squared, is pi over 3. And then solve for c. Okay, so I can multiply both sides by this square root, and I get that 1 is equal to pi over 3 times the square root of 1 minus c squared. Now I could move the pi over 3 to the other side, and I get 3 over pi is equal to the square root of 1 minus c squared. I could square both sides. If I do, I get 3 over pi, quantity squared, is 1 minus c squared. I'm getting close. Let me move over here. I can move the 1 to the other side, and I get 3 over pi, quantity squared, minus 1 is equal to negative c squared. Multiply both sides by negative 1, and I get that 1 minus, I'll just square this, so this is 9 over pi squared, is equal to c squared. Then I could take the square root of both sides, and I get that the square root of 1 minus 9 over pi squared is equal to c. And technically it's plus or minus, right here. But I need it to be in between 0 and 1/2. It can't be negative. So I'm not so worried about the negative square root here. I'm just worried about the positive square root. So this should be the C value that gets the job done. Okay? Very good. Any questions on that one? Let's see. Okay, somebody asked online for number 39. So number 39 says mean value theorems and graphs. So by visual inspection, locate all the points on the interval -4 to 4 at which the slope of the tangent line equals the average rate of change of the function over the interval. Okay. So in other words, what are the endpoints and what's that slope? And then can you kind of say, where is it going to be that slope? At other points. So 39. There are two endpoints. One of them is -4, 1. Is the first endpoint. And the other endpoint is 4, 4. Okay, so these are the two endpoints. It's a nice continuous differentiable function. So the mean value theorem applies. So I can say that there is a point C where the derivative of the function at C is equal to y2 minus y1 over x2 minus x1, which is 3 over 8. So there's some point in between where the derivative is 3/8. And so the question is, well, where is that? Or you could just kind of draw the line on there. The function looks kind of like this. I don't know. So it kind of comes down, touches here, goes up here, right? Something like this. Okay, and you're trying to say, well, where is the slope of this curve the same as that line? Well, again, I'm just kind of ballparking this, but it's kind of like it's in here somewhere, and it's over here somewhere. So you just kind of have to eyeball it on your graph. It's not going to be perfect. And kind of say, well, what's that x value and what's that x value where the slope of the curve is equal to the slope of the secant line. And if I were to look at their graph, I would say, you know, it's like at about 2.75 and maybe at about, I'm sorry, negative 2.75 and about 2.5-ish, somewhere in there. It's not going to be perfect the way they drew their graph. But the point is we can kind of recognize that there are some points in between where the slope of the curve is the same as the slope of that secant line. Okay? All right, I think that's a good place to end for today. So homework over mean value theorem is due today. The homework is already posted for L'Hopital's rule. That will be due on Friday, and we'll talk about it Friday. Then a review day on Monday, exam Wednesday and Friday in class. Okay? Have a great day. I will see you on Friday.
With the bar, right, when you said the 2.5.
I just kind of, yeah, I was looking at their graph. It's probably better than mine, but approximately 2.5. It's not obvious looking at it, but that seems about right.